Right, everyone, welcome. This is the final part of the topic on acylation, and today I'm going to be talking about acid anhydrides. So just having a quick look at where this fits in terms of our specification. So for AQA, acid anhydrides, we want to talk about the structures of them. So we'll be looking at those and also how we name them. The reactions in terms of how the acid anhydrides react with water, alcohols, ammonia, and primary amines. Look at how we're going to do an acylation reaction in order to manufacture aspirin. Fortunately for this one, we've no mechanisms to do, so it's all just reactions and structures and things like that. So let's just crack straight on with these. Okay, so structure-wise, so think about where the acid anhydrides come from. As the name implies, it comes from some acids. So let's say I've got some ethanoic acid. So two identical acid molecules. These react together to form our acid anhydride and releasing some water in the process. So they're always going to be identical. So therefore, what we're going to make over here is a symmetrical anhydride. Okay, so this is the anhydride. So how do we name them? Well, naming is pretty easy. So what we're doing is going to take the acid name, remove acid, and add anhydride. So my example above here was ethanoic acid. So it was an acid. We're now going to rebrand it over on this side to be ethanoic anhydride. Okay, nice and straightforward. So, quick another example. So let's go and take something a bit crazier out. Okay, I'm going to have two of these. I'm going to react them. So what am I going to form? Over on my left here, I've got 1, 2, 3, 4, 5 5 carbons, so therefore it's pentanoic acid. Over on this side, it's going to be the same, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and we're going to replace the acid with anhydride. So now let's look at some reactions. So the first two we're going to look at is water and methanol. So we can see I've got over here ethanoic anhydride. I've got 2 carbons on each leg, so it must have come from ethanoic acid. So it's ethanoic anhydride. Reacting it with water. So this is almost like the reverse reaction that we looked at on the previous page. So when we were forming the anhydrides. So what happens here is this is going to break it down back into our acids. So I'm going to make 2 identical ethanoic acids. One of those sort of pointless reactions, but does demonstrate that these things can hydrolyze, so they can break apart if they're left in aqueous solutions or waters present. Right, more useful one now. So I've got my ethanoic anhydride again here. So we'll put our names down. So I'm showing it with methanol here. So this could be any alcohol that you want to choose. but I'm just keeping things simple now just to make it a bit easier for me drawing them. So what happens here? Well, we're going to make an ester now. So now I've made a methyl ester of my anhydride. And what's left over is going to be some ethanoic acid. So let's name these things. So here I've got a methyl ester of ethanoic acid. So it'll be methyl ethanoate. And over here I've got ethanoic acid. So general terms, anhydride plus alcohol reacts to make an ester and a carboxylic acid. Right, moving on now, we're going to look at the reaction of the anhydride and ammonia. So I'm going to start with ethanoic anhydride again. And my reaction is with ammonia. I'll move to a green pen. NH3. Well, just like with acid chlorides, now these reactions are all essentially the same in terms of the products that we're going to be making, or the main organic product that we're going to be making. So, if we remember with our acyl chlorides, when we reacted it with ammonia, we made a amide. So this would be NH2. And my leftover material over here would be some ethanoic acid. So let's have a quick practice at naming these things. So my example is my ethanoic anhydride plus ammonia reacts to make 1,2-ethanamide and 1,2-ethanoic acid. So in general terms, what do we have? We have an anhydride plus ammonia reacts to give an amide and a carboxylic acid. So let's make our amine a bit more interesting, and we're going to stick alkyl group on it. So I'm going to stick with ethanoic acid for my ethanoic anhydride, I beg pardon, for my anhydride, like that. And this time I'm going to make CH3NH2. So now I've got a substituted amine here, or an amine for that matter. Right, so I'm reacting these together. What am I going to make? Well, I'm going to have my ethane bit here, okay. Then I'm reacting onto this, my amine. So now this nitrogen here is connected to 1, 2, 3 different atoms, and my side material that I'm going to make is going to be my acid again. There we go. So let's name these. Ethanoic anhydride. Now remember what this one is. Methylamine, methylamine, methylamine. Pronounce it as you like, as long as you spell it correctly in your exam, it doesn't matter. Okay, so now we've made an N-substituted amide. So I've got methyl group attached to my nitrogen, which is then attached to my carbonyl section. So my carbonyl section is my main bit of naming, so 1,2-ethanamide, because it's an amide, and we've got a methyl group at the start. So it would be, and I'm going to quiz you, make sure you know what I've done wrong. Methyl ethanamide. So what did we do to enable us to always know that our methyl group is attached to the nitrogen? Or we put our N-methyl ethanamide so that my nitrogen tells me that the methyl group is attached to my carbonyl group. And I've got some ethanoic acid again over here. I've been slightly out of focus at the bottom of my screen. My camera's not very good for this. So my general reaction, for you to remember, so I've got my anhydride. I'm reacting it with my amine. I form an N-substituted amide and my carboxylic acid. So we're going to move on to the preparation of aspirin, and this is sort of a nice common example of something that we can make. We can make this sort of stuff relatively easy, and you might very well do this in your practical lessons. So aspirin, this is it's a painkiller. It's a non-steroidal anti-inflammatory, if you're interested in that kind of thing. It's used to treat some heart conditions. It's a very versatile painkiller. Not really as popular now as it used to be, certainly 30 years ago. But it's still produced in quite large amounts. And what we make this from is from substance salicylic acid. So salicylic acid, I'll draw the structure in a minute. It's commonly used to treat warts, so it sort of rots off warts relatively simply. And there's probably other uses as well, but that's the only one I could think of right now. And what else we've got? And we've got ethanoic anhydride. Okay, so those are the two things that react together to make my aspirin. But why don't we use an acid chloride, I hear you ask? Okay, so we would get the same product. Okay, it would happen quicker. Well, it means that this stuff is a bit more nicer to handle, safe to handle. It's less vigorous reaction than an acid chloride. So because it's less vigorous, it will happen a little bit slower, less exothermic, and also we don't produce hope you remember what we produce as a byproduct, HCl. Okay, and why is HCl bad? Well, it's a corrosive gas. So let's crack on and we'll have a look at some of these structures. So we have salicylic acid. Oops. And salicylic acid contains a benzene ring. Okay, hopefully you're getting familiar with seeing these, even though you may or may not have covered it yet. Depends at what point in your career you were watching this video. So salicylic acid, as the name implies, it contains an acid, a carboxylic acid group there, and we also have an alcohol group attached to it there. And we're going to be reacting it with ethanoic anhydride. So this is CH3. So a little symmetrical molecule here. So remember, these things are going to react with water, going to react with alcohols, amines, or ammonia, as far as we're concerned in our A level. So we're going to look over here. Where do we think it's going to react? We've got an OH group there and an OH group there. The OH group over here is not an alcoholic OH. This one is an acidic OH. So our reaction point is going to be here on the alcohol. So it's directly bonded onto the benzene ring, but this is going to react as if it is an alcohol. So let's move on, join our products. So the acid remains unchanged. Okay, make sure my bonds go in there. I tend to get a little bit lazy with my benzene rings. And then joined onto over here, I've got my O, but this time I'll have joined on one part of this molecule onto that oxygen there, and I'll have some leftover CH3COO and an H that came off the salicylic acid. So let's just call it aspirin and ethanoic acid. So in summary, what have we learnt? Well, we know that anhydrides are formed from carboxylic acid, and they're going to be identical carboxylic acid. So two carboxylic acid molecules react together to form one anhydride. We name them by taking the carboxylic acid name, by removing the acid, so remove acid from the name, and then add anhydride in its place. Ethanoic anhydride, propanoic anhydride, 2-methylbutanoic anhydride, whatever it's going to be. And we've also discovered that they react in the same way, or at least to make the same products as the acid chlorides. And when I say products, I mean the same organic product. But they are safer. There is no HCl as a byproduct. And HCl, if we remember, is a corrosive gas. That's a gas, not a yes. And we can use them to produce carboxylic acids in the reaction with water. Why you'd do that, I don't know. We could use it to produce an ester, an amide, and an N-substituted amide. And we've looked at how aspirin can be produced. So we could have used ethanoic, anhydride or ethanoic chloride. Ethanol chloride, I beg your pardon. But we use the anhydride because it's cheaper and safer. Okay, hopefully this is okay as a quick sort of wrap up of this acylation topic. As always, if you have any questions, give me a shout and I will endeavour to help. Take care, goodbye.